Welcome back to our DC circuit series. So far, we've talked about quite a few basic circuit principles, theories, and tools, but today, I'd like to move into a theory that ties all of these together, specifically the Maximum Power Transfer Theorem. This theory explains how power moves through a circuit, and while commonly referred to with solar charge controllers, it has a very broad application. Before we jump in, I want to thank Digilent for supporting this lesson and the entire DC course, working with us to make these lessons possible. Now, I'd like to start with a simple question. Why don't devices always draw the maximum possible power from their source? Why can't a solar panel or audio amplifier just push out everything if it can all the time? This has to do with how power actually transfers from a source to the load. So, power is simply the rate at which energy is delivered, or how fast electrical energy is converted into something useful like light, heat, or motion. If we look at it mathematically, we know that power is voltage times current. But intuitively understanding the relationships between voltage, current, and resistance reveals a lot more about how power behaves. Even though resistance isn't part of that mathematical equation, it plays a huge role in power transfer. Every real power source, such as a battery, generator, or power supply, has some internal resistance. It may be small, but it's always there. This internal resistance means that some of the source's voltage is dropped inside the source itself before it even reaches the load. That's why a flashlight gets dimmer as the battery drains, even when the measured voltage still looks decent. So let's imagine a simple circuit: a battery, its internal resistance, and a load, such as a light bulb. The total voltage divides between the internal resistance and the load resistance. If the bulb's resistance is too small, most of the voltage drops inside the source, so the bulb gets little power. If the bulb's resistance is too large, the current drops to almost nothing, and again, the bulb doesn't get much power. There's a sweet spot, a point where the bulb receives the maximum possible power from the source. That's the heart of the Maximum Power Transfer Theorem. Officially, the theorem states that maximum power is delivered to the load when the load resistance equals the internal resistance of the source. In other words, the load and source resistance must be matched. This same principle is at the core of maximum power point tracking with solar charge controllers. In a solar panel, the voltage and current change with sunlight and temperature, so the controller constantly adjusts the electrical load seen by the panel to match its internal resistance at that moment. By doing this, it ensures the panel operates at its maximum power point, delivering the most power possible to the batteries or inverter under changing real-world conditions. Let's use an example. Let's suppose a battery has an internal resistance of 5 ohms, which for most batteries, but not all, is quite high. If we have an equal load that has 5 ohms of resistance, that load receives the maximum power the source can provide. Make the load smaller or larger, and the delivered power drops off. You can visualize this as a curve that rises, peaks, and then falls and tapers off. But this peak happens exactly where the two resistances are equal. However, there's a catch. When the load and source resistances are equal, half of the total power is lost inside the source itself as heat. This means that efficiency, or how much of the total power actually reaches the load, is only 50% at that point. So an important point to emphasize here is that maximum power does not mean maximum efficiency. If we increase the load resistance beyond the source resistance, the power to the load drops, but efficiency improves because less power is wasted inside the source. This is where it depends on the situation. What matters more, higher efficiency or higher power transfer? So, in communication systems like radios, matching impedances between transmitters and antennas is essential. That's how you get strong, clear signals, because you want maximum power transfer even if it's not the most efficient. This is generally the same approach with audio amplifiers as well. But in power distribution systems, efficiency is the most important thing. Utilities would never design for 50% efficiency, since that means that half of all generated power would be turned into heat. Instead, power lines and systems are designed so that the load resistance is much higher than the internal resistance, maximizing efficiency even though absolute power transfer is lower. It's important to understand that the maximum power transfer theorem isn't a strict rule, it's just a design guideline. It shows us where the trade-off lies between power and efficiency. When the load equals the source resistance, power is maximized, but efficiency is 50%. As the load increases, efficiency improves, but delivered power decreases. The right balance simply depends on your goal. Yet, understanding this principle helps engineers design everything from audio amplifiers and communication systems to power grid and renewable energy setups. I want to thank Digilent again for their help in developing this lesson, and you can best support us by going and learning more about Digilent. If you found this video helpful, please give it a like, subscribe to our channel, and we will catch you in the next one. Take care.
Hey, I hope this tutorial was helpful. Did you know that CircuitBread.com also has more useful engineering content? In addition to the tutorials, textbooks, tools, and other things, we have dozens of EE FAQs that explain quick, standalone concepts that are helpful for electrical engineers. Go check them out.